Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Fugacities in Gaseous Mixture. So, till now what we have seen most of the aspects related to the non-ideality of the system and then fugacity calculations for the different types of equations of state, those things we have seen. In other words, whatever the required things are there in order to calculate the fugacity of a real system, real gaseous system, we have almost covered all aspects related to that, so that we can calculate the fugacities for a given problem. Okay. So, now what we do, we see a few example problems or real life problems associated with the fugacity calculation, so that from fugacity calculations, if we can provide some kind of information like precipitation, condensation, etc., occurring those kind of processes, we can apply these principles and then check how much information we can get applying the principles that we have studied, right. So, that is what we are going to see, but however, before that what we see, we have a kind of recapitulation what we have seen. So, we have seen that if we know the equation of state in different forms, we know that pressure explicit form or volume explicit form, then fugacity of component I in the mixture you can calculate using appropriate principles. Let us say if you have a volume explicit form equation of state, then this equation you can use in order to get the fugacity of component I in a mixture where the Vi bar is nothing but partial molar volume of the that particular component in the mixture. If you have a kind of component I as a kind of pure component, then you can use here this equation to get the fugacity of that particular component pure I, and then here Vi is nothing but molar volume of that particular component. If equation of state, if you have in pressure explicit form, that is pressure terms are in one side and then all other rest of the terms other than the pressure are in the right hand side, then for a component I in the mixture, the fugacity you can calculate using this equation, where here dou P by dou Ni as per the equation of state we have to substitute and then simplify the equation. If you have a pure component I, then this P by Ni you have to substitute here and then integrate this equation and get the expressions. So, these are the generalized equation irrespective of what kind of equation of state we are using kind of thing, right. Okay. So, these are very generalized one. Now, depending on the equation of state, you can apply and then obtain a kind of fugacity expression generalized to each group of equation of state. Okay. So, let us say for van der Waals equations or gases which obey van der Waals equation, we have seen what are the expression for the fugacity. Similarly, Redlich-Kwong equation we have seen, Payne-Robinson equation we have seen, and then we have also seen how to obtain the constants associated with this equation of state using the corresponding state theory, etc. Those kind of things we have seen, right. If it is virial equation of state, so then corresponding expressions you can substitute here or here and then get the required fugacity information. So, for virial equation of state also we have seen how to obtain the virial coefficients, etc., from the intermolecular potential as well as the corresponding state theory, those things we have seen. So, that means almost all information we have in order to find out the fugacity of a component I in a mixture or a fugacity of pure component I as in the kind of pure form. So, those things we can do now. So, now we can apply these principles on real life problems. Now, what we do before solving some real life problems, we will be discussing how to obtain generalized expression for fugacities of a component I or J in a mixture if the mixture obeys virial equation of state, right. For the mixture, if it obeys the virial equation of state, then we know the virial equation of state is nothing but Z mixture is equals to PV by RT is equals to 1 plus B mixture by V plus C mixture by V square and so on. So, we are taking only second and third virial coefficient, and then higher virial coefficients we are not taking for simplicity. Okay. Also, one reason is the simplicity, another reason is that information on those higher virial coefficient from the experimental studies is almost negligible. For B, that is second virial coefficient, we have enough data for a majority of gases. C also we have a very few data for pure gases, for mixtures even less information is available. So, that is the reason we are taking only up to C, that is third virial coefficient. Now, here this equation what we have to do, we will be writing this equation in a pressure explicit form, that is pressure will be having one side and all other terms will be writing other sides, and then this generalized expression for fugacity of component I, whatever is there, RT ln phi I is equals to integral 0 to infinity dou p by dou Ni T V N j at constant T V N j minus RT by V dV minus RT ln z. This expression we have already seen actually, right. So, this expression now we what we try to do here in place of dou p by dou Ni, according to Virial equation of state, what is this dou p by dou Ni, we will be finding out and then substituting here. Okay. So, for a Virial equation of state, if you write only up to third virial coefficient and write in pressure explicit form like this, then we can write P is equals to RT by V plus B mixture RT by V square plus C mixture RT by V cube. Now, this expression here, what we have to find out? We have to find out what is molar volume. This molar volume we have to write in terms of total volume divided by NT, total number of moles. So, for that what we do initially, now we take a for two component system, capital V divided by Ni plus Nj as total number of moles, because only binary mixture we are taking. So, this information we use here, then pressure can be written like this. Okay. This and then this is nothing but B mixture. We have already seen that B mixture is nothing but Bii Yi square plus 2 Bij Yi Yj plus Bjj Yj square. This is what we know, and then Y we can write it as Yi, we can write it as Ni by Nt, and then Yj also we can write Nj by Nt, like this we can write. So, then we have this expression. Similarly, C mixture also we have mixing rule for Virial equations, that we have written like previously, Yi cube C triple I plus 3 Yi square Yj C double Ij plus 3 Yi Yj square Ci double j plus Yj cube C triple j. This we have, this is also we have seen. So, accordingly here also for Yi you write Ni by Nt, and then Yj you write Ni by for Yj also you write Nj by Nt. So, then we have this expression. So, now this here, this Nt square, and then this Nt cube we can cancel out. Then we have this expression P is equals to RT by V multiplied by Ni plus Nj plus RT by V square, and then all this expression is there. Now, if you partially differentiate this P with respect to Ni, because for ith component we are doing. So, when you take with respect to Ni, Nj is constant. So, dou P by dou Ni would be RT by V multiplied by 1 plus 0. So, that is RT by V, and this is RT by V square. Differentiation of Ni square with respect to Ni is 2 Ni. Here differentiation of 2 Ni Nj with respect to Ni is nothing but 2j, and differentiation of Nj with respect to Ni is 0. So, then third term is not there. So, likewise differentiation of all other terms we are doing here for this third term in the RHS as well. Then we have this one. So, now this dou P by dou Ni information whatever we got here for Virial equation of state, that we are substituting here in the generalized expression. This is the generalized expression irrespective of which equation of state it is. From here onwards, depending on that equation of state, expression will change. Okay. So, for this Virial equation of state, dou P by dou Ni, we have found it like this. This is dou P by dou Ni minus RT by V is there. So, RT by V cancel out, dV minus RT ln z. Right. So, then RT and this RT also if you cancel out from either side. So, this RT is gone, this RT and this RT with the RT in the left side, left hand side if you cancel out. So, ln phi I in the left hand side, the integration of this particular 1 by V square is minus 1 by V. So, minus 1 by V 2 Ni Bii plus 2 Nj Bij is there, 2 also we are taking as a common. Same is integration of 1 by V cube is minus 1 by 2 V square will be having, and then remaining terms integration remaining terms would be constant, right. So, then here next step what we are doing, we are taking we are substituting this V 2 infinity limits in either of the terms, and then we are also taking 3 common from this second term of the RHS. So, that we have a 2 by V Ni Bii plus Nj Bij plus 3 by 2 V square Ni square C triple I plus 2 Ni Nj C double Ij plus Nj square C I double j minus ln z is as it is, we are not doing anything with that one. So, if you generalize this one ln phi I for multi-component system, what you get generalization as well as writing in terms of the molar volume. So, now what we do before generalization, you can see here we are writing in terms of a molar volume, that is coming because whatever Ni is there, that in order to get the Ni as a kind of Yi terms, what we are doing, first term in the RHS here we are multiplying and dividing by Nt. So, Ni by Nt is Yj and Nt by V is nothing but 1 by V, this is what we get. So, 2 by small v we are getting here. Similarly, here also what we are doing, we are multiplying and dividing by Nt square, so that Ni square by Nt square is Yi square, and then Ni Nj by Nt square is nothing but Yi Yj we get, and then Nt square by V square is nothing but 1 by small v square. So, that this is what we have here, 2 by V small v Yi Bii plus Yj Bij plus 3 by 2 small v square Yi square, then C triple I plus 2 Yi Yj C double I j plus Yj square Ci double j minus ln z mixture, this is what we have. So, this is for the binary system. If you write it for a multi-component system, so the first term would become 2 by V as it is, this would be sigma Bij Yj, j is changing from 1 to m, and then if there are m number of components are there, right. Similarly, here second term 3 by 2 V square would be as it is, and then sigma j is equals to 1 to m, sigma k is equals to 1 to m, Yj Yk C I j k minus ln z mixture. Let us say if j is equals to I and then k is also equals to I, then what should be this first term? It should be Yi multiplied by Yi, that is Yi square, and then C I that is C triple I. So, that is the first term here like this. Okay. So, like that we can generalize this, and then third term minus ln z mixture. So, this is for m number of components that are present in the system, and then whereas this one is for the binary system having 2 components I and z, right. So, this equation I have written here again for the requirement, because now this equation we expand for 2 components binary mixture I and z are 1 and 2. Then for component 1 we can write this equation ln phi 1 is equals to 2 by V y1 b11 plus y2 b12 plus 3 by 2 v square y1 square c triple 1 plus 2 y1 y2 c double 12 plus y2 square c 122 minus ln z mixture we get. Similarly, ln phi 2 we get this expression, right. So, this equation, what is the limitation? It is valid for moderate densities only, because we know that virial equation of state is valid for the low to moderate densities only, though at high densities we can apply, but it gives some kind of errors because of non availability of this virial coefficient at high densities. Okay. This equation 1 may also be applied to any number of component, not necessarily for the binary, right, without making any assumptions about the mixing rule that we have seen. So, we do not need any mixing rule here. Okay. Further, theoretical calculation of various B and C coefficients from statistical mechanics is restricted to relatively simple substances that we already know, alright. Plenty of information is available for this B and C for simple molecules, but for complicated molecules there is some information, but very small little literature is available, right. So, despite of that one, this equation number 1 is also valid for non-ionized molecules, polar, non-polar kind of complex molecules. For all those things it is applicable. Okay. But only limitation is though it is applicable for other kind of molecules also, that limitations may be you may be finding difficulty in using this equation only in terms of what is the corresponding B and C, second and virial coefficient for those molecules. That limitations you may be having, but equation point of view it is valid for complex molecules as well. Further, data for second virial coefficient B is sufficient data is available, but whereas for the third virial coefficient very small data is available, and further higher virial coefficients data is very negligible, right. So, considering this region that for C data is very small, if you take this equation only up to second virial coefficient, then what we have, we can get this expression ln phi I is equals to 2 by V sigma Yj Bij minus ln Z mixture, because information about third virial coefficient is very less. So, we are not taking, it is not 0, no information or little information, very small information is available. In such conditions, if you truncate or if you do not take the third virial coefficient in virial equation of state, then you get this expression. Okay. We have this Z is equals to PV by RT is equals to 1 plus B prime P. So, this equation we can write V RT by P plus B prime P RT by P. So, this is cancel out, right. So, but B prime we know it is nothing but B by RT. So, then we can write this expression as V is equals to RT by P plus B mixture. So, now small v we can write it as capital V by Nt, small v is molar volume, capital V is the total volume. So, Nt if you take to the right hand side, so then we have RT by P Nt plus B mixture Nt, right. B mixture we know that this is BII Yi square plus 2 Bij Yi Yj plus Bjj Yj square, that is what we are having. So, then Y's if you write N's by Nt, then you can have this expression for the B mixture. Then we need dou V by dou Ni in order to substitute in the expression RT ln phi I is equals to integral Vi bar minus RT by P dP, right, that is the generalized expression. So, there we need Vi bar is nothing but dou V by dou Ni. So, if you do that one, so you have this expression, okay, RT by P plus this expression whatever this particular term, if you do the differentiation with respect to Ni, you will have this expression, right. Further, if you simplify, this term will become 2 Bii Yi plus 2 Bij Yj minus B mixture. So, this particular part entire thing is nothing but we can write it as B mixture. This particular part divided by Nt square we can write it as B mixture. Okay. So, now if you substitute this dou V by dou Ni, whatever this expression that we are having, right here, then you integrate it, this RT by P is cancelled out. Then we have ln phi I is equals to 2 Bii Yi plus Bij Yj minus B mixture P by RT, this is what we are getting. Okay. So, for binary mixture this is what we have, I and J component, that is we have taken. But if you have a multi component system, multi-component system if we are having, then we can generalize this expression as ln phi is equals to 2 sigma j is equals to 1 to m yj bij minus b mixture p by RT. This is what we are having. Okay. So, whether you write volume explicit form or pressure explicit form for this virial equation of state, so then we have a corresponding Figasti expression now for this equation of state as well. So, now we can go to solve a few example problems. Now, whatever the just obtain expression equation phi in terms of ln phi, when you write V as volume explicit form, then we find this equation is it is more convenient to use. Why? Because in this equation we have pressure as independent variable, which is much convenient to use in general, right, for any equation of state. Further also it is preferable because in the virial equations C primes if you neglect, then it provides better approximation to the Figacities rather than neglecting C is equals to 0 in virial coefficients, right, because that is inducing more error. That is what it has been found by the experimental observation, right. C prime you can neglect by neglecting C prime neglecting in the sense you are writing Z is equals to 1 plus B prime P plus C prime P square and all that P series we have written. So, there it is inducing less error if you remove or neglect the C prime. But in the form Z is equals to 1 plus B by V plus C by V square, in that form the C if you remove, so that may induce large error in the subsequent calculations. So, that is the reason also the equation number 5 that we just derived, that is better to use as well as the reliability is better. Further, in the limit as component I becomes infinitely dilute in component j, then what will happen to the equation number 4, that we will see now, right. See that equation number 4 is for the binary system. For the binary system we have written this equation number 4, okay. 2 by V sigma yj bij minus ln z mixture we have to see, we have taken for previous case. Now, the component I becomes infinitely dilute in component j, that means yj tending to 1 and then yi is tending to 0. So, then phi I would be tending to phi I infinity, okay. So, that means I component is very small, then ln phi I we get here in this equation, this is nothing but what we have y1, let us say for ith component this should be yi bii plus yj bij. So, now what happens, this yj is 1, but yi is 0. So, what you have yj bij you are having, only that much you are having, and then this yj is also tending to 1. So, that means yj bij is nothing but bij or close to bij, and then this since it is a j is a lot or large amount close to tending to 1. So, what we can say, V mixture is also equals to molar volume of pure j, okay. Similarly, Z mixture also close to the Z pure j, okay. So, now what happens in such kind of system, let us say I becomes infinitely diluted in component j, that means you can say that is almost it is like a pure j component. Then in general people may think that whatever the results like parameters associated to those pure j are also valid for the mixture, that is let us say whatever bij, it is a cross virial coefficient, right. So, but when you say that j is large, almost pure j is there, though it is a mixture of I and j, I is very small, j is very large. So, then you may be thinking that the bij may be close to the bjj, but that is not in general, right, that is not in general. So, we can see here, so in that ln phi expression bij is there, it is very much important. So, if you wanted to obtain the Figasti coefficient of I, though it is present in very small amounts, very small amount, you need to have a kind of very accurate reliable information about this cross virial coefficient bij. You cannot take simply Bij is close to Bjj. Indeed, we are going to see one example and then we realize that Bij is very much far away or different from the Bii, Bjj, right. So, repeating that even the system is very dilute system, I is very small, negligible amount is there, J is very large amount is there. Under such mixtures also this cross virial coefficient Bij is going to be very much important one, and then this Bij you cannot approximate as close to or almost equal to Bjj, considering that it is almost pure J. Though it is almost pure J, you cannot say that Bij is approximately equals to Bjj. That we demonstrate now using an example problem. So, consider a binary mixture of species A and B which obeys virial equation of state at 127 degree centigrade and 80 bar. At this temperature, second virial coefficients of pure component are given, BAA and BBB are given. BAA is nothing but the pure second virial coefficient for pure A, BBB is nothing but second virial coefficient for a pure B component. Okay. At infinite dilution, that is as Ya tends to 0, the Figastic coefficient of A, that is phi A infinity is given as 1.08, then estimate what is the cross virial coefficient BAB. That is BAB is nothing but cross virial coefficient for the mixture, it is not for the B mixture, it is the cross virial coefficient required to obtain the B mixture. Since Ya tends to 0, Yb tends to 1 here. So, then B mixture whatever Ya square B double A plus 2 Ya Yb Bab plus Yb square B double B is there. So, this we can write approximately B double B because Yb is close to 1 and then Ya is 0. So, first two terms are almost 0. So, we can write approximately B mixture is equals to B double B, right. So, then we need a Z mixture, because that equation we are going to use to get the cross virial coefficient is having Z mixture term. So, Z mixture is nothing but it is given as 1 plus B mixture P by RT. So, B mixture is now you obtain as or approximated as 101 because it is a kind of pure this thing. Then you have a Z mixture is equals to 0.7571, right. And then if you have Z mixture, you can find it out V mixture as Z mixture RT by P. When you do this one, you get V mixture as 314.7255 centimeter cube per mole. Actually, up to this part, we have already seen in one of the lecture, finding out only Z mixture and V mixture, right. Now, next level to this one, if you wanted to obtain the cross virial coefficient, so you have to use this expression. Because now here Z mixture is known, Ya, Yb are given, Ya is close to 0, Yb is close to 1, Baa are given, and then this one you have to find out, Bab you have to find out. Even ln phi ln phi A infinity is also given. So, now from here this expression for this problem what we get, we can have ln phi A infinity is equals to 2 by V. Ya is almost 0. So, we are not taking, Yb is almost 1. So, you can take it as a kind of 1 and then Bab minus ln Z mixture, right. So, now ln phi A infinity is given as 1.08, 2 by V we obtained this one, Ya is 0, Yb is 1. So, and then Z mixture you got 0.7571. So, then here Bab you can see it is minus 31.677 centimeter cube per mole. Now, it is very different from BAA or BBB because this BAA it is given as minus 16, BBB is given as minus 101 centimeter cube per mole, and then BAB we got it as minus 31 roughly approximately. So, how much different it is from BBB or the second virial coefficient of pure B is far away, I mean very different, right. So, the cross virial coefficients we cannot take based on the consideration whether it is a dilute system or not, we have to follow the principles whatever available. Okay. we have the other approach also, we have other equation also, depending on in which form we are taking the equation, that Virial equation of state. Other form we are having ln phi I is equals to 2 sigma yj bij minus b mixture p by RT. Now, here also if you take Ya tends to 0, Yb tends to 1, then you have ln phi A infinity is equals to this expression. So, Ya is 0 here. So, this term would be there, Ya is 0 here. So, Ya is 0 here, this term would be there, and then Yb is equals to 1. So, then what we can write, ln phi A infinity is equals to p by RT 2 b AB minus b double b, if you take Yb is equals to 1, this is what we can write. So, now here also phi A infinity is given, p is given, t is given, and then b double b is given, that is second virial coefficient of pure b is given. So, then we can obtain BAB, only unknown, from this equation. So, that can be obtained as minus 34.5 centimeter cube per mole. So, now we can see here average geometric average, if you see, if you take geometric average also, in the worst case, if the things are not available, then you can take the geometric average. So, BAB, if you take square root of BAA, B double B, so it is coming minus 40.2 centimeter cube per mole. So, now you can see here, previous case, what we have, it is approximately minus 32 we got in the previous approach. This approach we got BAB is approximately minus 34, and then good thing to see, the geometric average, it is giving minus 40, not very bad approximation considering the problem that we have. It is almost close to the values that we got for the by two different approaches. So, in the worst case, when there is no information to find out cross virial coefficient, if you know the pure virial coefficient, then we can find out cross virial coefficient by geometric average. This should be BBB, right. So, now we take another example problem. This problem actually we have seen in one of the lecture. This problem what we have taken as a kind of a example to find out the virial coefficient, cross virial coefficient from different types of correlation that we have developed from the corresponding states of theory. So, those correlations we have used to find out the cross virial coefficients and then virial coefficients for pure systems, etc. So, now in addition to that, we will be finding out now the fugacity of those components, okay, two components, and then further we try to find out what is a real problem. Can we get some information about the real problem? The real problem is that we have a 1 mole gaseous mixture, within which 1 mole percent is CO2 and then 99 mole percent H2, and then assume that this gaseous mixture obeys the virial equation of state, and isothermally at minus 100 degree centigrades, isothermally at minus 100 degree centigrade, this mixture is compressed to 60 bar, so that to check whether precipitation of CO2 occurs or not. Out of this mixture, CO2 and H2, we wanted to make H2 much more pure. So, what we are doing, we are compressing this mixture to check whether this CO2 is being compressed and then taken out as a kind of solid form or not. Once it is compressed as a kind of solid form, then we can easily separate it out from the H2. So, that H2 will become much more pure, that is the purpose, right. So, that is what we wanted to check, whether the first of all, if we compress isothermally at 60 bar, is it going to be precipitate or not? If it is precipitating, how much it is precipitating, that we have to find out. So, we have to use the virial equation of state. So, corresponding fugacity expression we have to obtain, right. So, because the virial coefficients are not given. So, this problem, the data is given, Tc, Pc, Vc for both the component are given, and then omega also for both the component are given. So, using the correlation that we have seen in one of the previous lectures, so we will be finding the virial coefficients, and those virial coefficient would be used in ln phi I expression that we have derived today for virial equation of state. So, for precipitation to occur, what should be the condition? So, precipitation in the sense it is initially gaseous mixture is there, that we are bringing to the solid state. So, the chemical potential in the vapor phase, if it is high, then that will be transferring from high chemical potential to the low chemical potential side, assuming the solid side or the compressed side is in kind of low chemical potential, then precipitation will occur. So, what we have? We have a gaseous mixture, right. Now, we are compressing so that there is a precipitation occur. If this has to occur, so the certain component for CO2, right, CO2 we are finding out. The CO2 chemical potential of CO2 we have to find out, or fugacity of CO2 we have to find out for either phases, because they are equivalent. So, gaseous phase, let us say FCO2V we call it, for solid after precipitation if at all occurring, FCO2S let us call. We have expression for pure condensed component. What is the fugacity expression we have? So, we can find out this one. And then gaseous mixture, it is given that it is given that virial equation of state is being obeyed by this gaseous mixture. So, for the virial equation of state, just now we have derived a expression for fugacity coefficient. So, fugacity in the vapor phase also we can find out. So, if the chemical potential of this component is low in the gaseous mixture, so it cannot go from low chemical potential to the high chemical potential side. So, the precipitation will not occur, right. If the chemical potential of CO2 in the gaseous phase is high, so then it is possible that from high chemical potential to the low chemical potential side, that is solid side, it can go. So, then precipitation occur, right. So, you have to find out the chemical potential, or chemical potential is much more clearly related to the fugacity, and then you have to check which side, which phase for this particular component fugacity you have to measure, and then depending on in which phase it is high. If it is high in the solid phase, so then it will not precipitate, because it is already high viscosity, high fugacity solid state. So, from high rather precipitating, it may be going into the vapor state, gaseous state. Or if the fugacity of this CO2 is high in the vapor phase, so from high fugacity level to the low fugacity level, the transfer of species will take place, right. So, then under such condition precipitation will take place. Okay. So, we have to find out these two information, and then after finding out these two values, then only we can say whether the precipitation is occurring or not. Once we know the precipitation is occurring, how many moles out of the given total moles we can find out how many moles are being precipitated, that can also be found. Okay. So, indirectly what has to be the condition? FCO2 in vapor phase should be higher compared to the FCO2 in the solid pure compressed solid state. Okay. So, for solid phase pure and then assuming this compression is taking such a way that only CO2 is precipitating, H2 is not there. So, that we can say that the solid phase is pure of a CO2 if at all precipitation is occurring. Okay. That is the assumption. Okay. Only CO2 is being compressed, precipitated if at all it is occurring, and H2 is not being precipitated. Under such assumption, what we can say, if at all precipitation is occurring for the solid phase, it is going to be a pure CO2. Okay, pure solid CO2. Okay. Then we have already derived this expression long back in second or third week for pure condensed phase, the fugacity you can find out using this expression. What we have? We have this VCO2S is given as 27.6, or molar volume of CO2 under the saturated conditions is given 27.6, and then P is given as 60 bar, and then saturation pressure of CO2 is given as 0.1392. In the problem statement it is given, otherwise we have to find out from the textbooks, or we have to use the Antony equation at this temperature, whatever the minus 127 temperature is there. At that temperature we have to find out corresponding saturation pressure from the Antoine equation using the Antoine constant ABC. So, now everything is given here, R is known, so T is also given. So, you can find it out this value as 0.11486. So, then FCO2S would be nothing but whatever PCO2 saturated is nothing but 0.1392 exponential of this value 0.11486, that is 0.156 bar. So, the fugacity of CO2 in the solid precipitated form at this temperature of minus 100 degree centigrade and 60 bar. Temperature is minus 100 degree centigrade, not the 127. Okay. At minus 100 degree centigrade and 60 bar, the fugacity of CO2, if at all it is precipitating in a pure solid compressed state, it is having 0.156 bars of fugacity. The same thing we have to find out for the vapor also, that is gaseous mixture. For the vapor, what we have, virial equation of state we are having, right. So, we know that FCO2V is nothing but YCO2 pi CO2 V P. YCO2 is given only 1 mole percent of CO2 in the total mixture that is present, okay. And then P is also given 60 bar. So, pi CO2 V, if you find out, then you can find out whether how much is FCO2 V by using this expression, and then depending on this value how much it is, you can decide whether precipitation is occurring more or not. If this value FCO2 V is higher than the FCO2 S, then precipitation would occur. Okay. So, but in order to find out this one, we have to use the Allen-Fea expression for a virial equation of state that we have derived just now, right. So, that expression, if you write for a binary component, whatever the expression is there, that you expand for H2 and then CO2. So, we need only for CO2, H2 we do not want. So, we do not want to calculate anyway. So, Allen-Fea CO2 V is equals to 2 by V Y CO2 B CO2 plus Y H2 B H2 CO2 minus ln Z. Y CO2 is nothing but mole fraction of CO2 in the mixture, and then Y H2 is nothing but mole fraction of H2 in the mixture. B CO2 is nothing but second virial coefficient of pure CO2, and then B H2 CO2 is nothing but the cross virial coefficient of H2 CO2. So, how to find out these things? Without this information, we cannot solve this problem. But in one of the previous lecture, we have found this thing using the correlations, because for these components TC, PC, VC, omega, these information are available. So, that we have used, and then we found these coefficients already. So, but however, I am putting them here once again as a kind of recapitulation. So, for CO2 we have used this correlation by Scher and Pitzer, right. So, here C1, C2, C3, C4 are functions of omega, right. Omega is given for CO2, and ZC is function of again function of omega. So, ZC you can find out. TR is nothing but T by TC. TC is given, T is given as minus 100 degree centigrade. So, then that TR you can find out. So, except C1, C2, C3 everything is known here. C1 we can find out using this correlation according to them, like C2 also we can find out, C3 and C4 also we can find out. Then when you substitute this information here in this expression, all this information if you substitute here in this expression, then you will get BCO2 as minus 495 centimeter cube per mole roughly. I am just going forward quickly, because this problem we have already solved in one of the reaction, only this part of the problem, that is finding cross virial coefficient. Similarly, for H2 we have this correlation by Goodwin and co-workers, that is BH2 is equals to B1 x power 1 by 4 plus B2 x power 3 by 4 plus B3 x power 5 by 4 plus B4 x power 7 by 4. This B1, B2, B3, B4 are constants are available as per this correlation, and then x is also given as per correlation 109.83 divided by T, T should be taken in Kelvin. When you substitute all these numbers here, then you will get BH2 is approximately 8.8269 centimeter cube per mole. and for cross virial coefficient we will be using the Maclaurin correlation. So, that is given like this here. So, we need TC12 and then V12. So, these things TC12 we know that square root of TC1 TC2, VC12 is nothing but 1 by 8 of 1 by 8 multiplied by cube root of VC1 plus cube root of VC2 whole power 3, then we get V12 is this one, right. So, if you substitute this information here in this expression, you will get B12 as, next TR12 is nothing but 1.73, and then B12 by TC12, if you use this expression TR12 expression in previous this correlation, in this correlation here, this T by TC12 is nothing but TR12. So, that information if you use here in this correlation, TR power minus 1, TR power minus 2. So, that we use here, and then VC12 also we got. So, then BH2CO2 or second cross virial coefficient of H2CO2 at this temperature of minus 100 degree centigrade is nothing but minus 24.5462 centimeter cube per mole. So, you have all the information, and then in the mixture this CO2 is present in very small, only 1 mole percent, right. So, then we can say that whatever the mixture is there, almost pure H2. If you take that logic, then you can say Z mixture is nothing but ZH2, and then V mixture is nothing but VH2, because these two information we need in order to find out this Figasty ln phi CO2 V, that expression we need V mixture and Z mixture also. So, we do not have any other way of calculating it except using the problem logic of the problem given, that is the CO2 is very small. So, then we can take remaining component H2 as a kind of dominating in the mixture. So, that mixture may be approximated as a kind of a pure H2 in order to guess this Z and then V for the mixture. So, ZH2 is equals to 1 plus P BH2 by RT, BH2 we got 8.8 something, P is 60 bar, T is minus 100 degree centigrade. So, then we get ZH2 as 1.0367. Similarly, VH2, if you have ZH2, then VH2 we can write it as ZH2 RT by P. ZH2 is 1.0367, this is R, this is T, this is P. So, VH2 will get 248.520 centimeter cube per mole. So, now we got all information to find out ln phi CO2 V. V also, V mixture we got, Z mixture we got, cross virial coefficients and pure component virial coefficients also we got. So, substitute them here, then we get phi CO2 V as 1.3118. So, from here FCO2 V is nothing but YCO2 phi CO2 V P, that we got. So, then YCO2 is nothing but 0.01, right, and then phi CO2 V is 1.3118 and then P is 60 bar. So, then you get FCO2 as nothing but FCO2 V is nothing but 0.7871 bar, and then it is very much higher compared to the FCO2 S. So, the precipitation will occur. Okay. So, now we found precipitation is occurred, but how much it occurred? If that you wanted to know what is the mole fraction, of this particular component in either of the phases at equilibrium, we have to find out. We have seen that these are not equal, FCO2 V and FCO2 S are not at nor they are not equal. So, then we realize that the precipitation has occurred, some process compression has taken place. Okay. But otherwise not necessary that if you maintain the constant temperature and then increase the pressure, all the system will go some kind of compression. It depends on the system to system. For this system, the compression of CO2 has taken place. So, if you wanted to know how many moles of compression has taken place, you have to know the composition at the equilibrium, right. So, at the equilibrium what we know, FCO2 V should be equals to FCO2 S. FCO2S is a constant one that we already got it as 0.156, and then YCO2 is nothing but and then FCO2V is nothing but pi CO2V P. This is what we know. So, then from here we can find it out, YCO2 is equals to FCO2S divided by phi CO2V P. So, P and then phi CO2V is nothing but exponential of 2P by RT YCO2 BCO2 plus Y2 plus YH2 BH2 CO2. This is what we got, right. So, now here if you substitute this for the mixture, whatever the YCO2 etc., all these mixtures for the mixture composition, if you substitute 0.01 and then 0.99, then you will be able to find out what is the YCO2 at the equilibrium. Whatever the inequality is there, because of this YCO2 is going into the different phase. So, how much it has gone? So, you can find out by this one. So, that is 0.002037 is coming. If at all it is equilibrium, no precipitation has occurred, so then YCO2 we should have got back to the its initial value of 0.01. If the no precipitation has occurred, only gaseous phase is there, so then YCO2 has to be 0.01 by the at equilibrium as well. But at equilibrium YCO2 is not equals to 0.01 of initial value, it is much lesser, 0.002. So, that means some amount is there that is being precipitated, okay, that we have to find out. So, by this way also we can find out that precipitation has occurred by comparing the YCO2 value at equilibrium with the YCO2 in the feed or the initial YCO2. Initial YCO2 and then YCO2 at equilibrium are not same, that means some change, transfer of the species has taken place, okay. Now, here transfer of species is taking place from a gaseous phase to the compressed CO2 phase. So, now assume precipitated solid is pure CO2 and let N be the moles of CO2 left in the gas. Then from mole balance, for 1 mole of mixture we can have this expression that whatever the YCO2 at equilibrium should be equals to N by N plus whatever the mole fraction of other component. Then you can find it out N as nothing but 0.002021. These many moles are left in the gas out of 0.01 moles of CO2. Total 1 mole of gas is there, out of which only 0.01 moles the CO2 were there, but after this compression only 0.002 moles of CO2 is remaining. So, remaining amount whatever is there, remaining amount 0.008, approximately 0.008 moles of CO2 has been precipitated. So, this is how we can solve any real life problem. In the next lecture we will be taking a few more examples to understand how to make use of this FIGAST information to solve a few real life equilibrium problems. Okay. So, the references for this particular lecture are given here: Engineering and Chemical Thermodynamics by Koretsky, Molecular Thermodynamics of Fluid Phase Equilibria by Prosnit et al., Chemical, Biochemical and Engineering Thermodynamics by Sandler, and then Introduction to Chemical Engineering Thermodynamics by Smith et al. The problems that have been solved here are the kind of exercise problems given in this particular book. Also, the virial equation of state, their corresponding FIGAST expressions are also provided in this particular book, all these things. So, this is going to be important reference book for this particular lecture. Thank you.